This is the Physics 2211 Lab 3, where we find the mass of a black hole. The purpose of this lab was to use the data of a star's motion that was given to us in a CSV file to determine the mass of a black hole that it is orbiting. So we do this by using VIDLE and VPython, as well as our knowledge of Newton's second law, and the universal law of gravitation, the position equation, and the parallel and perpendicular components of FNet. Then we will address what-if questions and what does it mean questions. Then discuss the source of error and come to a conclusion. Well, the conclusion that I came to was that the mass of the black hole was 3.3835 times 10 to the 31 kilograms, which is approximately 17 times the mass of our sun. These were the equations used. The top two we've seen before. There's Newton's second law and the position equation. The third is one of the more important ones, the universal law of gravitation, and it was mainly rearranged in order to find the mass of the black hole, and we'll see that a little bit later. Then below that is FNet equals FNet parallel plus FNet perpendicular, and also dp/dt equals dp/dt parallel plus dp/dt perpendicular. And in this case, those two are equivalent. And generally, these were modified in order to fit them into the VPython code. These were the initial conditions that were given to me by WebAssign. The star's mass was 1.989 times 10 to the 30 kilograms. The delta T was 86,400 seconds, otherwise known as 1 Earth year. And the black hole's position was -2 times 10 to the 10 in the x component, 5 times 10 to the 10 in the y component, and 0 in the z component. Here we can see the results of the model. The FNet magnitude was 1.941 times 10 to the 27 newtons. The FNet parallel magnitude was 5.407 times 10 to the 26 newtons, and the FNet perpendicular magnitude was 1.866 times 10 to the 27 newtons. And the picture on the right we'll expand upon on the next slide. So we can see here a simplified version of the model that we saw in the previous part, and it looks similar, but it's not the same, but I've used it in order to explain what's going on here. So the yellow circle is the star, the black circle is the black hole, and the green oval is the approximate orbit. So the red arrow is p hat, and this shows the direction that the star is moving. Now, if the black hole were to disappear and the FNet became 0, the star would continue off in this direction indefinitely. The black arrow is FNet parallel, and this is pointed in the opposite direction of p hat. Now, it would always be on the same plane as p hat. In this case, because it's pointed in the opposite direction, this means that the star is slowing down. The blue arrow is the FNet perpendicular, and it will always be perpendicular, or 90 degrees, from FNet parallel and p hat. This points towards the center of the quote-unquote kissing circle. The yellow arrow is FNet, and it will always be pointing towards the black hole. Now this is the sum of FNet parallel, FNet, and FNet perpendicular, and it is vector addition. Here we'll use an augmented law of gravitation because we know what each of the values are in the law of gravitation after we run our Python code, except for the mass of the black hole. Therefore, we can rearrange the equation to solve for the black hole's mass. Although we can solve for the mass of the black hole on paper, it's easier for the computer to do it for us. So we put the law of gravitation in code format, and we let it print it out at the end. And we found the mass of the black hole is 3.3835 times 10 to the 31 kilograms. So what does it mean? The FNets are the forces on the star. The forces are the cause of the PDTs. The perpendicular, parallel, and net components of the change of momentum match up with the same components of the force. In this experiment, we can approximate the force to the change of momentum because the masses stay constant. So what if the black hole was replaced by another black hole at the same location and the motion of the observed star due to the black hole was unchanged? Would we be able to tell the difference? And the major hints to the answer are in yellow, and that would be no. There would be no way to tell, because if the motion is the same and the location is the same, then the F-nets are going to be the same, and therefore the mass will be the same according to our equations. So there are not very many possible sources of error. However, one is that if the CSV file was open, which mine wasn't, it could round down numbers, leading to less accuracy. Another is that a slight syntax error in the code could lead to a major change in the model. I dealt with this in particular where my y component of velocity wouldn't generate, causing a cascading effect, making the forces and mass to be completely incorrect and errors to not show up correctly in the visualization. This was remedied by simply adding a +1 to a particular part of the code. So, in conclusion, by using VPython instead of given data, I was able to insert appropriate equations into the code frame in order to calculate the force components and magnitude of the force, which ultimately allowed me to compile all of the outputs into a modified universal law of gravitation, which solved for the mass of the black hole. And this mass was 3.3835 times 10 to the 31 kilograms, or approximately 17 times the mass of our Sun. Thank you for watching.